All right, it looks like a lot of us are already on, and so we'll go ahead and get started. Thank you all so much for coming. Good morning. I'm Chloe. I'm with the Tri-County Regional Energy Network, and today we've got Andy Pease and Jennifer Rennick from Inbalance Green Consulting with us for this great lecture on renewable energy, energy storage, and resiliency. This is our second time hosting this lecture. The first time was during a really great happy hour we had a few months ago in Santa Barbara. And I'm curious how many of you maybe heard about this webinar from maybe a friend or colleague who attended that happy hour. So if that's the case for you, I'd love to hear about it if you want to pop it in the chat or email me later. My email is going to be at the end of the presentation. But if you're hearing about a happy hour and you're like, this is totally new to me, what are you talking about? It was a really great event series we had last year that we're probably going to be doing again this year, where we brought Imbalance in and a few of our other instructors to do some in-person lectures. So if that sounds interesting to you, make sure you're on our email list and that you are keeping an eye out for when we relaunch that this year. And before I pass things off to Andy and Jennifer, I've got a few intro slides to get through, but then we'll get to the topic. You can go on to the next slide when you guys are ready. Thank you. So I know a lot of you have probably seen this slide before, but we always like to start with this and just explain a little bit about who we are and what we're doing here with all these great lectures. So we're the Tri-County Regional Energy Network, and the regional energy networks are funded by ratepayer dollars. Essentially, this means that on your utility bill, you are paying a little bit into a public good charge, and historically, the utilities got to keep all of this money, and they used it in the utility hubs, so essentially not in our region. And then about 10 years ago, local government said, we want to take some of this money back and use it more effectively for the people in our neighborhoods and our communities. And so that's how the RENs were born. And so now we get to use some of that money and take it away from the utilities and use it locally to benefit you all. And so that being said, I am a public servant. I work for the County of Ventura. We want to be doing things that help you guys. So if you have any interest in an offering that we don't currently have at 3C Ren, let us know. We're always interested in doing new things, hosting new kinds of events. And you can always email me. My email again will be at the end of the presentation today. And so outside of great lectures, we also offer a few other things through 3C Ren. We have our incentives for multifamily and single-family properties, as well as commercial businesses, and technical assistance for farms, as well as critical facilities. Go to the next slide. Thanks. And then lastly, before I pass things off to Andy and Jennifer, I just wanted to let you all know that our incentives are back. We have incentives available for all of our programs. So that's commercial buildings, multifamily properties, and single-family properties. And we have incentives for anything that might be energy saving in your home or business. So this includes HVAC, water heaters, even insulation. So if you have any questions about what could be covered, you can always email us and we will get that information to you. Okay, and so with that, I will pass things off to Andy and Jennifer. Thanks so much, guys.
Great. Thanks so much, everyone, for joining. We're excited to be here. Jennifer and I are both architects, and Jennifer is a certified energy analyst. I'm a lead accredited professional, and we're delighted to partner with 3C Ren to be able to provide continuing education. Here's the learning objectives for those of you who are submitting for or achieving, earning AIA or ICC credits. I just want to clarify that the learning units is 1 hour, and 3C Ren is kind enough to allow an hour and a half in this time slot so that we have plenty of time for discussion and questions. But we get your time is precious, and if you need to jump off after an hour, we understand and won't be offended. So we'll go ahead and jump into the course. We're going to be starting off with terms and energy use in context, just to set that baseline, talk about the grid to the building scale solutions, and then go through kind of best practices and regulations for solar panels, chemical batteries, and then talk about managing client expectation, particularly in the residential sector, but in general. And then Jennifer has a great round of resources that are available. You will get all the slides at the end, so so don't worry about having to take copious notes. And I'll be whoever is speaking, the other one is going to be monitoring the chat. And so we'd love your questions throughout. If it's a longer answer, we'll save it for the end. But if we can knock out some questions along the way, that is awesome too.
Okay, thanks, Andy. I want to say on the learning units, I didn't type in specifically the ICC units, but I believe, Chloe, this class does count also for ICC. I think so.
I think it might just be AIA, but I will find out and I will put the answer in the chat in a few minutes.
Okay. All right. Okay, I'm gonna chip in with some terms and kind of give us a little bit of background of building energy use, but our overall energy use in the big picture and down to the building scale. And when we talk about renewable energy, batteries for energy storage and other types of energy generation, there's some relatively new terms that are popping up that I hear folks kind of throwing out there, and other people don't quite know what they mean. Some of it's coming up from the industry itself. Others are is from the policy side. So I wanted to highlight a few terms and just put some definition to it, because some of these things overlap with each other, which can add to the confusion. So when you're doing some research and taking a look at like the literature on energy systems, solar, battery, etc., you might see the acronym DER, and that stands for Distributed Energy Resources. And really, those distributed energy resources, DER, it's just a shorthand way of referring to, and it's usually small scale, referring to your local solar system, like on your roof, or, covered parking, your battery storage system. It could be combination heat and power, if you have a fuel cell, if you have a small wind generator, etc. And all that can feed a specific local building, for example, location, or it can feed back to the grid. And by grid, I mean the grid that attaches, the electric grid that attaches our power plants to our individual buildings and everywhere in the state and beyond to the rest of the country. So a microgrid is essentially an electric wire electric energy system that can operate independently of the bigger grid that we think of. And it can be part of that bigger utility grid, or it can function on its own. But the thing with a microgrid that makes it different than just talking about these distributed energy resources itself is the microgrid is self-contained in the sense that it has its own monitoring system and its own controls, and it includes its own infrastructure. But that microgrid itself would include the energy production, like solar panels, and could have storage capacities like battery. And so that microgrid could be an individual house, or it could be multiple buildings that are interconnected to have its own microgrid. And then microgrids use distributed energy resources, because that's what feeds the microgrid is your battery or your solar power. But certain DER or distributed energy resources could be somebody's microgrid. That is then, a particular building's or location's microgrid could be a resource that could be tapped for a bigger DER. So that's kind of why some of these terms get conflated and can be confusing. Islanding specifically when you hear that term, it's really referring to the ability of a microgrid that can operate independently from the greater utility grid. So, for example, you could have a whole community of homes, a neighborhood that is part of a microgrid, and when the, say, PG&E power goes down, if you're in the PG&E area, that neighborhood microgrid could keep operating because of its own solar and battery and infrastructure system. And so then the transition is seamless. And a lot of times microgrids are kind of what happens on people's individual house. It's a little microgrid where their house and battery, their solar panels can operate independently. And then a virtual power plant, you might see that VPP, especially residential scale, because your battery storage system might be part of a virtual power plant, which means that there's a utility demand response. And so when needed, your battery could feed back to the grid to help alleviate stress on the grid when other areas of the grid's power is down, like during high windstorms. Then all the folks that have their batteries as part of that virtual power plant, the utility will have the demand response, and then those can feed back into the grid and help alleviate some of that part of the grid that needs power. Purchase power agreement, a lot of folks have heard of that, a PPA. That's when a third party, like Sunrun, for example, would own and maintain the solar and sometimes solar and battery system for a predetermined cost. And so you pay that PPA for the energy that that solar system is producing, but the third party owns and maintains and really takes care of the battery and the solar panels at the end of their life as well. So they're responsible for all that. And sometimes this is a good way for folks to get solar or batteries if they couldn't afford it outright or don't want the upkeep and maintenance of the system. So similar to that, the new term, well, it's been around for a few years, but I'm starting to see it now bubble up into more common conversation. So as architects too, you might hear this, and that's an EaaS, or energy as a service. So it's like a PPA. So a third party owns and maintains the whole microgrid and the associated equipment for that whole system. And they take care of all the energy produced by the various distributed energy resources and the controllers for it. So for example, Schneider, and this is a great, it's a good resource, and it shows a good visual example. And there's other companies out there doing this, but for example, Schneider Electric has a microgrid system, and now they're have an operating system that helps folks monitor and maintain all the various components that could go into their microgrid, which is a utility connection. It could be solar, you could have natural gas generators, you could have wind, batteries, takes care of electric vehicle charging, and your lighting and HVAC and other plug loads in the building itself or multiple buildings. And that way, a third party maintains, monitors, and takes care of all the equipment, which for some businesses, that is a really good service because they don't have in-house expertise to monitor all this and to make sure everything is up and running and operating at peak performance. Now, how we kind of all got into this as a state or local communities really started on the national scale in the 1970s. And so NREL, for example, National Renewable Energy Laboratory, was started in 1974. It began operating in 1977 as the Solar Energy Research Institute. So the idea of using solar and then building on that for our electric grid has been with us in our country for a long time. And in California, following kind of in line with what was happening on the national level, we in California adopted an energy code in 1978, and we created a California Building Standards Commission. And the idea was to reduce the energy consumption, especially in buildings, and thereby then reducing the need to build more fossil fuel power plants. All in the meanwhile, at the national level, we were developing photovoltaics, and the whole idea was to get that cost down to $1 per watt, and thereby making it affordable for people, municipalities, communities, small scale, large scale, start to use solar energy as a non-fossil fuel, reduced carbon form of creating electricity. So on the California building sector, kind of looking at California specifically, we have a strategy that I think of as like a part 1, part 2, part 3 strategy. So part 1 is energy efficiency in buildings. Okay, so a lot of it, we teach classes on all that. You can take some of those courses, but we follow the energy code, passive systems before active. We look at high efficiency equipment, et cetera, et cetera. The part 2 was we have better electricity generation. So we have PV systems on site. Now, per code, depending on the occupancy, you might have to have a small PV array as part of your building, but there's also the grid scale with solar, wind, hydroelectric, et cetera. And then the part 3 is the energy storage. And there's different kinds of energy storage. Some of it's like chemical batteries, where we think of battery energy storage systems, BESS, but there's also large scale batteries that have to do with pumped energy, such as pumping water up to a higher location and then allowing that water to flow through back down to the lower reservoir, creating electricity along the way. And there's other long duration storage solutions. Where this takes us, this part 1, part 2, part 3 is something that we noticed in California and in other states, but we began to see that as we added renewable energy to our grid, and we used that to offset the demand of electricity from the grid, over the past decade, our need for electricity in the middle of the day was met by solar production, which was a good thing. But when this is mapped out, for example, the lowest net load day of each spring for the years 2015 through 2023, this map shows that pattern of energy use for the lowest use day for our state. The whole thing resembles what looks like a duck. So it became known as the duck curve. And what the duck curve was indicative of is that we were reaching a point where on many days of the year, California was producing more solar energy than we had need for at the time. And what to do with that energy that's being produced by those solar panels, the idea is we store it so that we can use it when we need it later in the day. Because what happens when the sun goes down between 6 and 10 p.m., folks are getting home, their buildings everywhere are having the lights turned on, communities have street lights, people's heating and cooling systems were being turned on and there was a huge peak in electricity demand, and the sun wasn't shining. Okay, so that's kind of the duck curve story. But California and many other communities have a plan for how to work with it, and a lot of it had to do with battery storage. So I pulled 2 days, October 22nd, 2025, October 24th, 2025, from the California ISO grid mix, just to get an idea. And so the most of the kind of the teal color at the bottom was our large hydro systems. That's how much energy was being produced and used. And then the blue, it was natural gas. Wind is the green. Batteries is the purple. And we also import energy from the surrounding grids as needed. And the gold was solar. And so if you were to subtract the solar contribution, you would see that it resembles that duck curve, that kind of a shape. So down at the, it's when the sun shines in the middle of the day, when the sun's highest, we get a lot of solar contribution to our system. Otherwise, and then that means that some of the other resources are contributing less. And then our batteries kick in the early morning or in just afternoon to help alleviate that duck curve. And so on some days, we have a lot more wind, and maybe it's stormy. So we have maybe less solar, more wind, but the more wind we have, the less natural gas we need. And then on some days where the wind doesn't burn as much, wind isn't blowing as much, like on October 24th this last year, then more natural gas was used to create the rest of the electric energy that we needed. And a lot of times where we have a lot more solar, then we're having clear weather. So we're not having so much wind, but we also don't need as much natural gas if we're having a lot more solar contribution. So really what this kind of mix tells us is that when solar and wind aren't available, we make up the difference in California, typically with natural gas power plants. So California has many power plants are called peaker plants, and these burn natural gas. They create electricity. And this one, for example, in Oxnard, it's mostly running in that 4 to 9 p.m. time slot to kind of make up for that extra boost of electricity we need when the sun isn't shining. So they're built to meet those peak demands. Now, as California is adding more energy storage and can take that extra solar energy, put it into battery storage, and put that battery storage into the grid, then other natural gas power plants that were burning kind of throughout the day, we don't need them. And so a lot of those are being retired. And so the air quality in our grid is getting cleaner in California as a result. So that's kind of that big picture. Now, how buildings sort of fit into this, I'll give you some examples here as we kind of go from that grid solution to the battery scale solution. And this just to give you kind of a visual idea and take a big picture down to the small, and then we'll have some examples of what we see in our local buildings. So as California continues to add solar panels in the grid,
Sorry, just going to interrupt. We have a lively chat going on, and so I
Oh,
just
cool.
wanted to check in on a couple of loose ends. Some are about battery chemistry and applicability more at the building scale, so we'll talk about that a little bit later in the presentation. There are some questions about costs, and you note the $1 a square foot was the goal for I don't know now
Yeah,
if
a
it was
dollar a watt was the goal back in
sorry,
the,
foot, $1
yeah,
a watt. And the question came in, well, how much is it now? I don't know when you get a chance I mean, I think it's a few bucks, but I don't actually know what the cost per watt is right now. So,
it depends. And some of them are as low as like $2.83. And some of them around $4.50. So yeah.
depends on the watt and the scale and all of those things. So, but more than $1, but of course there's inflation from that. So,
Right.
terrific. So I think we'll go ahead and keep going and be able to jump in on some of the other questions as we go through it. Thanks.
Okay, perfect. So big picture for California is, okay, by March of 2024, California, part of the analysis was they could say, yep, 69% of our mix in California, the energy grid, was non-fossil fuel sources. So yay, it was the tipping point. We're more than half of our energy was not from fossil fuels. And the whole point of that is to reduce the emissions, reduce our dependency on it, use the fossil fuel, but I mean, use our oil and our natural gas strategically and still have resources available to maintain a good price point on that as well. So it kind of all, fits together as we want to reduce air pollution, make neighborhoods that had those big gas powered plants, and we took off all the coal burning plants because those for sure had far more emissions than the natural gas plants. And so by there, we're cleaning the air, making those neighborhoods more livable. Plus, it actually reduced, even though electricity prices and inflation creep up, overall, it actually reduces the price of our electricity generation to have renewables. And so of the renewable resources, 38% of that mix was provided by wind and solar. So that just kind of gives you a scale of what the impact is now. And then when it comes to what was happening in California, California Energy Commission, that same kind of commission that was regulating our new energy codes, building codes, they always are doing research and studies and improving California. And so this report, I just thought it was great that this report, was part of the 3C REN area, but Mission Produce, Oxnard, California, at their avocado packing facility was one of the microgrid analysis case studies they did. So they have the solar PV and special type flow batteries. And then they were monitoring and looking at that and giving assessment and really talking up how we can use microgrids for more sustainability. Community scale solutions. An example of this would be where farms are adding PV systems to their farming operations, known as agrivoltaics, depending on where you're from and how you say it. There's two different spellings out there for that. But the idea is that there's a lot of land that we have that can be used for agriculture, but it also can be used to produce energy. So there's different ways of doing it. So some farms are experimenting with having their solar panels mounted absolutely vertically bifacially and running it north-south. So as you'll get sun on one side in the morning, then the sun moves over, you'll get the other side in the late afternoon, but it keeps the panels upright so that farm equipment can get down through the aisles, for example. And then this particular farm had the pleasure of being on a tour for the American Solar Energy Society this summer. And here they had two different sizes of panels, heights, and kind of looking at cost effectiveness and whether it was better to have 8-foot tall or 6-foot tall, and the implication for the equipment and the farm operations and the birds, etc. So I expect to see a lot more of this type of use of PVs and farming. And then, of course, there's community spaces that are now embracing microgrids and energy. And so if you want to get a look at what that is like, if you haven't been to the Santa Barbara Botanical Gardens Conservation Center, they have a really nice outdoor seating area that gives you a close look at what the bifacial solar panels look like. And then I included an aerial shot just to show you kind of what that looks like, as they have a lot of panels also on the roof, and then that surrounds their HVAC mechanical well. Santa Barbara has really been working hard as a city entity to be more sustainable. So if you're not familiar with what they've been doing, I recommend you go to their website, because they have created some microgrids that are there for the city to be more resilient. So for example, one of their microgrids is at the Granada parking garage, but it not only generates power for the garage and the surrounding offices, but also the 911 call center, and also helps with the electricity at the nearby central library. And more libraries are being used as emergency spaces and cooling centers for people. So this microgrid then can island and still maintain energy for those emergency entities. And then they also have another great battery system that they've put in for their treatment facility plant. So yeah, take a look at those. You could go visit the parking structure and see it yourself. And then as we go down in scale, multifamily buildings are all, and at least the ones we work on, we see a lot of emphasis on the multifamily projects, especially the affordable ones, going all electric, and then having the ability to have as much solar on the roof as possible, and then sometimes surrounding parking spaces, so that that solar can be used then to heat their hot water through heat pumps, and to heat and cool the building through their ductless and ducted mini split systems, heat pump systems. And then Santa Barbara County Office of Emergency Operations, their last expansion for their new dispatch center also included large solar canopy arrays, and that feeds in their battery. And then they also have diesel backup generator, but they mostly set this up to be dependent on the solar and then the batteries, and then the diesel generator in emergencies if they've depleted all their battery and solar. And that just gives you kind of the idea, the scale of that and what's going on in our community. So those are a few places you could visit. Andy's going to jump in right now and just kind of follow up with like what this can look like on the individual house scale.
Thanks, Jennifer. Appreciate that. And as you can see, we're talking energy storage, and resiliency at all scales, because all of them are going to matter. The one that's often approachable for the individuals is to think about our homes and what zero net energy really looks like, it means. And so in that sense, zero net energy, even before we're talking about storage, is the concept that a home is going to generate generate as much energy from their solar panels over the course of a year. So, and we would think about kind of over generating in one season, and then being able to collect on the off season. So your electric meter would run forwards and backwards, depending if you're over generating and under generating. So PVs, where it's a standalone, great investment, but the net energy metering system has been updated to reflect changes in the grid and what the grid needs. And so what that means is that in order to really have a cost-effective solar array, you're going to want to have batteries. So here you can see a home with kind of a scale. So you can see, code is going to require solar panels, maybe 8 to 10, depending on the house and the climate zone. If you want to go Z&E, you're going to want more solar panels, and even more if you have an electric vehicle to charge. And then you can add that battery storage system. It adds both the resiliency and energy independence if the power goes out, but it also adds cost effectiveness so that you can shave that peak load in your electric system. So here's an example in a Atascadero, 2,000 square foot home, which is climate zone 4, might need a 2.38 kilowatt system for the code compliance as a minimum. And then this is just kind of a diagram about the options when we think about solar in this capacity. So you're always going to have a meter. You're always going to have your main panel. That's just how homes are. The utility meter is going to the grid, and the main panel is covering every electric circuits to everything in your home. Then on the roof, or perhaps if you have a big lot on the ground mount, but you're going to have your solar panels and your inverters, right, to convert from DC to AC. And then those things come together. There's a power control device to be able to distribute the solar into the home. And then you kind of have a brains that's going to be able to determine what the load is in the moment. And then there's some smart circuits that you can do optional. So if you have enough solar, that you can power up the air conditioning and the pool pump and the EV charger. But the main things that you're going to want to make sure are hooked up to the battery. If you have a smaller battery than your total home load, then you're going to want to make sure that you're firing up your refrigerator, lights in key locations for exiting, and some outlets, particularly ones in the bedroom, so that you can charge your devices if the power goes out. And so just allowing enough space, if you're trying to put everything all together, by the time you have a battery and that gateway and the load center that manages that and your panels and a charger, you probably want like maybe 10 feet of clear wall space. And we're showing Tesla just because that's had kind of an early jump in the market, but there are lots and lots of brands available now, really good products across the board. So this is kind of allowing that space, but in practice, it doesn't all have to be clustered together. Here's an installation where just the battery and inverter and home load are in kind of one section. They're mounted outside under an overhang, and so protected, but they are outside and clustered. This one is a Tesla Powerwall and shows the capacity here and the size for you can wall mount or ground mount those. And then here's the kind of other half of the installation that has the main electrical panel, that gateway, kind of the brains of the operation, and then the sub panel that has those backup loads. In this case, they're backing up the whole house. But again, you could be select if you have a smaller battery situation. There's also some different combinations. So there's a solar and thermal energy storage to think about. This is a system that I have in my home. So I didn't need air conditioning. So I didn't do, often you'll do a heat pump for heating and cooling the home, and then a heat pump water heater for your hot water. In this case, you can take the heat pump water heater and use the hot water both for showers but also for heating the home. So a hydronic type of system. And the value there is that you can use that efficient heat pump during the day when your solar panels are getting their peak use. It heats up the water, and then the tank, that indoor water tank, is super well insulated. And so it's ready to go overnight and in the evening and overnight when electricity costs are high, right, and your solar panels aren't up. So this particular system is Harvest Thermal, and then they use a Sandin or Sanco heat pump hot water system, and then that's paired with a ducted air handler. So this is the installation in practice. The installation still in progress. So little heat pump mounted outside. It's very quiet, and then it goes to this tank in the inside. It's very into the tank itself. It doesn't have any electric controls. It's just a thermos. It's huge. It's 140 gallons because it's heating my hot water and heating the home. And then there's kind of this Harvest Thermal controller, but again, there's other brands that do that. And then it routes hot water to this air handler. And then I have just a ducted system and a smart thermostat.
And you like it.
And I like it. Yes. I like it for a couple of reasons. One, again, I didn't need air conditioning, so to be able to use one heat pump for the things that I do need. And I also like that Sandin, and we don't really get into refrigerants and heat pumps in this talk, but the Sandin uses a CO2 as the refrigerant, so that has the lowest of the global warming potential, which is a concern for me. And yeah, and it keeps us warm.
Yeah, global warming potential of 1, which is
right,
awesome.
versus like R410A or R32 or some of those other refrigerants, which we can talk about.
Right. And then, so that kind of gives you an idea. What we're trying to do here, big picture idea, is go, okay, our buildings fit into a bigger picture. There are individual buildings as architects, or we do plans examination, or a builder. We're working on individual buildings at a time, but then those could be part of the bigger group, like a microgrid that includes more than one building or a campus. And then bigger from that, we have the grid that feeds into those things. And what is our California grid doing to be cleaner, have more renewables? This is the path that California is on. And now we're going to take a look at just some of those best practices and some of the regulations to keep in mind as we are designing our buildings and looking at our communities. So the applicability of solar panels based on occupancy type of a building is regulated by Title 24, Part 6, which is the Energy Code. And these occupancy types includes high-rise residential, low-rise multifamily residential, grocery, retail, restaurants, schools, library, warehouses, et cetera, homes, hotel, motel. So there's a lot of occupancy types where now in California, a small amount of the energy load needs to be provided on site, just as part of, I think of it as like a social responsibility. It's like the building energy responsibility, the part of it. And under the 2025 code, which just took effect January 1st, we had some occupancy types were added, but mostly some of these occupancy types had a slight increase on their solar PV and battery requirement. Restaurants, for example, kind of had a dramatic increase because part of that also is that restaurants now have a electric ready component. And this is, again, just new construction. And when it comes to understanding how we as designers and builders are going to place the solar panels, or and how we can design for the solar panels, we have to keep in mind that our firefighters need roof access. So we use Title 24 Part 6 to dictate the size of the system required, but we can't forget about Title 24 Part 9 or Part 2.5, the residential code, because that's going to dictate our fire safety and our access. And so just kind of real big picture is the fire access must be capable of supporting firefighters and roof fire ventilation. So that's kind of the overriding concept for our code. And we probably don't have to say too much to know that this is on top of people's minds in California, is fire safety. And so part of that is our code's going to dictate the walkways, and they need to be located so they don't have a lot of obstructions. And then it's also going to have code language that talks about the PV system conduit and raceways and where their location is and where it should be installed. And again, this is so that there is an accessible roof free of trip hazards for our firefighters. And it's also just good practice for everyone else that needs to come up on the roof and do maintenance. Specific to the non-res and your R3 occupancy types, that's going to be dictated under Part 9, and that's section 1205. And so it dictates how wide those perimeters and those walkways are going to be. And what we're seeing, the reason I mention this is, yes, it's part of the sustainability solar batteries, but also why I mention it is because we're seeing more and more projects where their PV required size is kind of limited by how much roof they have and what solar accessible roof they have. And you need to make sure that you're really outlining for your clearances around your access panels, and to make sure that the PVs are not below an egress or an pathway, and that the aisleways are wide enough to meet code. And sometimes that is chewing into the space for the PV system size. So it becomes a balancing act for a project, whether they're meeting code or do they have bigger goals of zero net energy, or is it cost effective? And so we're seeing that interplay come into mind. And then specifically for residential roof installations, Title 24 Part 2.5, it currently is section R324 that talks about the walkway widths, and also specifically talking about your roof PV and how much of your PV system is covering the roof, and whether or not that's going to kick in a requirement for fire sprinklers. So reminder, you will get a copy of the slides. So I've just kind of bullet point highlighted a few of those key things for you. And then, of course, if you're working on a residential design, you'll need to go in and dig into the code specifically. But that's kind of FYI, keep in mind that if you are going for that zero net energy and you're covering a lot of the roof with panels, then it may also trigger sprinklers. Okay, when it comes to understanding a little bit more about batteries and where the code is going or has gone for 2024 and our 2025 code that took effect January 1st of 2026, understanding what chemistry the battery storage has is key. And kind of our old school off-grid systems. This still exists. I was just at a off-grid house in Colorado that are just using more current technology or current battery system, but it's still lead acid batteries. And they're still available. There's some maintenance required, but they have a low power density, but they don't have a lot of high cost as lithium, sort of the drop-in replacements have, but those are available. And then with a rise in demand for smart home backup systems, like Yeti, for example, came up with their Goal Zero, and there are other brands out there that are doing this, but the idea was that your home energy storage system would be modular, and so you could link more of them together and stack them, and you could connect your lithium battery to your old lead acid batteries, etc. So way back when, I was really familiar with Yeti brand because they were working with a lot of folks that were off grid before that became so common and popular. But as the battery chemistries became more energy dense, one of the ways to do it was to use lithium cobalt and other cobalt and magnesium chemistries. But it turns out that these battery chemistries were really flammable. So in 2020 and 2021, for example, LG Chem recalled all their 10,000 batteries, and that kind of forced the dialogue of like, hey, what are we doing if we really want homes or buildings to have energy storage? We need to find solutions that are not causing home fires, for example. So chemistry matters, and also where we mine those minerals and what's going on that scale matters. Now, one thing about the new batteries and the new battery chemistries is these batteries are recyclable. And so there are entities now that basically mine those minerals back out of the batteries, the existing batteries. And that means that there's less actual mining needing to be done in the ground for those same resources. So common battery chemistries of the most of the batteries we're seeing now. Lithium ion, by far, any sort of lithium type of battery is the most common, but some of them had thermal runaway as a possibility, and others of them are non-combustible. So now if you're concerned about that, and sometimes you don't have a choice, like if you go with the Tesla batteries now, if it's a Powerwall 3, you're automatically getting the lithium iron phosphate chemistry, which is non-combustible, and it has a high power density. Still uses and does not use cobalt. Okay, and then there's the lithium titanate oxide batteries, also non-combustible, has a little bit lower power density. It's also cobalt free. So those are the kind of the new chemistries that are out there. So batteries are improving and the fire is less of an issue, but you still might be dealing with some of the old battery chemistries, especially in the existing buildings that already have their batteries. Battery chemistries that are being developed right now, sodium ion and zinc ion. And so these are better environmentally. Sodium and zinc are both abundant in Northern California, and these are lithium and cobalt free when it comes to this type of battery chemistry. So look out for these. And some of these are example of some of the brands that are developing this. And then when it comes to the battery chemistries, and the allowable battery size for your building or your project. This is dictated by Title 24, Part 9 as part of the fire code and not the energy code. So, for example, this table dictates how much energy capacity, so that size based on the battery chemistry. So your lithium ion batteries, 20 kWh, kilowatt hour capacity. Okay. Now that was, you say, okay, but great. You just told us some of those lithium battery chemistries don't have thermal runaway and they're not combustible. So how come I can't use them? Well, so now under the 2025 code update that just took place, they have updated it to just say, okay, you've got the lithium ion batteries, but if you have some of these other battery chemistries that we just talked about that has the zinc or the sodium, then they are saying, okay, you've got the option to have a larger capacity there with the batteries. But right now, they're not differentiating on the different lithiums yet. And it's probably because it's a bit nuanced and confusing to differentiate really specifically on the different lithiums. So that gives you kind of an idea that under the new code, take a look, that limits your battery size. For the large scale battery energy storage, you do need a hazard mitigation plan that's required, and just architects, designers, or maybe it's your civil engineer that's dealing with your site design. When you have these larger scale batteries for commercial projects, you do need to pay attention to clearances above, the sides, the back, the front, and there are specific requirements depending on their location. To give you an idea of that, and if you want to see one, you could visit Stanford University up in Palo Alto, California area, and they have them as part of their bus fleet. So they have solar canopy above, then they have the battery storage, and Posh Energy is just one brand out there, but you could go to the website and also see what it looks like. And then these units give you an idea of the scale. The double doors, when they open, that box like 6 feet wide, it's about 7 feet tall, and they do have doors on both sides. That gives you an idea of the scale. The energy storage system permitting, or battery energy storage system permitting, BESS or ESS, depending on which section of the code you're reading, lays out the requirements that you have to have on your construction documents. So this is an excerpt from Chapter 12, Title 24, Part 9. For the 2025 code, it just more explicitly lists out the requirements, as saying a fire plan is also required with this. But even though already in what's the requirements, it does talk about your fire suppression, thermal management, ventilation, exhaust, etc., and a decommissioning plan, which is really key, because again, what happens at the end of the life of the battery? So that decommissioning is supposed to be part of your whole permitting process. And then those batteries should be recycled. For a small scale, just gives you an idea of what that can look like. It could be, ground mounted, outdoors, or indoors. And the big thing is to make sure there's a clear path of travel and that it's away from doors and windows. And the residential code then has some additional requirements and some specific requirements on your battery sizes. So the non-res requirements said in Title Part 9, Title 24, Part 9, kind of gave you limits on the capacity of those batteries based on their chemistry. And the residential code is looking at this based on its location. So, for example, you, depending on where it's located, is going to determine if you have to have type X gypsum, et cetera, if you have to have smoke alarms that are interconnected, et cetera, and how close the batteries can be near each other, and then how many of those batteries you can have all together. And so 2025 code now, you're going to look for that in section residential section 330. So they changed the section on us. And where you used to just say, no matter what, you could only have 80 kilowatt hours altogether. So 4 individual batteries, if each battery is a 20 kilowatt hour max. I mean, that's a lot of batteries, but now the code is a little more nuanced. So it really, and a new table to go with it, and it really depends on where it's located. If it's on the outside of a wall, and if it's on the outside of the wall and it's constructed with non-combustible surfaces, or for example, outdoors, but on the ground, and it's 3 feet away from property lines, is going to be different than if it's on the ground outdoors and 10 feet away from property lines, for example. And then with each of these kind of nuanced location requirements, you can have more and more batteries put together to meet your maximum battery size. And then also part of the code update is really looking at the location of the battery or the ESS, and whether it's on a sidewall or running parallel or perpendicular to parking, and what else is going on with the parking situation. So again, you're going to find that in the Part 2.5 residential code. And with that, I'm going to turn it back over to Andy to talk a bit about managing some of those client expectations and just give you a couple residential examples.
Thanks, Jennifer. And before we leave the battery section, there were a couple of questions that came up. One is about battery life. Like, what's the life expectancy of batteries at this point?
It depends on how many cycles of charge and discharge. And so the batteries are rated by their charge and discharge cycling. And so the batteries I have, for example, are part of a virtual power plant, and also they were designed to charge up during the day and to discharge at night. And so it's set to a certain limit, and it uses it up, charges it up, uses it up, and it's supposed to last 10 years. And then a new battery system will be replaced, and then should last another 10 years, and my panels are supposed to last 20 years or plus. So that's kind of the ratio.
Great. And then somebody asked if the batteries emit EMF, electromagnetic field.
Well, all things that are electric emit electromagnetic fields. All things electric do. And the batteries, they're just sitting there doing nothing until you need them. And then they create the electricity, and it feeds into the rest of the system. And then the whole electrical system is energized, but it's nothing more than just the rest of your electric system. It's not like
Okay.
you're under big power lines, where you can actually like feel it under the big grid power lines. It's nothing like that, because the electrical wiring for your home batteries and your solar system and your home electricity is all within the residential size and scale of wiring and Yeah, there's nothing unusual about it.
Great, thanks. There are a couple of bigger questions I think we'll save at the end. One about kind of batteries in a commercial setting as backup for even a fire pump. That's kind of a bigger conversation. And then there was a good question about the using your vehicle battery to charge to power up your home, and kind of where we are with that technology. But I think we can go ahead and finish the presentation and then save that for some chat at the end.
Okay, and that question, I'll hit on it really briefly in one of the resources.
Oh, yeah, great. Okay. And so we had touched briefly on designing that zero net energy home, and this is kind of just wanting to manage client expectations or your own. We had talked about how for a zero net energy home that it's over the course of a year, and so this is a diagram of a predicted your electric energy use over the year. And so in this particular setting where there's maybe not air conditioning, and so you have kind of higher loads for space heating and appliances and all of that during the winter, and lighting you need a little bit more of, and then during the summer months not so much, but you have that high solar production during the summer. And so traditionally, rather than having batteries, we use the grid for that, right? So that's part of the whole grid resiliency, is that the grid was the power company was basically buying up your extra solar energy in the summer and then giving you credit for that during the winter. So then you would have a once a year, and you still do have a true up bill. So you might only have like a little like, hey, here's $30 just to use our grid monthly charge. And then you might get like, $1,000 in April because that was your net at the end of the year. So you just got to make sure that people are prepared for that. And then there's for the homeowners, there's different ways to monitor. Now there's a lot of smart systems and you can use your app. You can also just physically see your inverter if it's like in your garage or someplace useful. You can see in the moment how much energy you're producing. This is an old install. Again, this is at my home, and at the time, my roof faces exactly east and west, and so in order to try to optimize the south, the installer was kind enough to do this kind of tilted panel. Now the panels are more efficient, and we also recognize that west-facing panels are super helpful because that's giving you that peak or the electric generation during those peak afternoon hours. And so this was an expansion to that system. And then you can see this is an example of a little readout that shows I have a smart panel now. So each of the circuits is tagged: the kitchen, the spa, that mini split that I showed you for the heat pump. And so I can see what the electric use is historically and in the moment. These are the solar panels themselves. And, unfortunately, I'm getting ready for a new roof. These panels are old. I've got a whole little pet moss farm going on under my panels. And so I'm going to be in that position where, is it worth taking my solar panels off and then reinstalling the old ones, or just ditching them because they've served their useful life and I just need to start from scratch? So I'm torn on that at this point. I hate to waste when they're still working great. And then here's another existing home, and this one a little bit more recent with a solar PV and battery system. This is Jennifer's home. We both like to guinea pig on ourselves, and you can kind of see all the parts and pieces. In this case, she did the PV, the panels, the inverters, and the batteries, and the vehicle charging, all in one component. And so here's the electrical panel getting the work done. And so just thinking about the considerations. That question about the roof, make sure that you've got a reasonably new roof before you add solar panels, or get the roof done first. Do you need new electrical panel? I kept my 100 amp panel. Jennifer was able to upgrade hers. And just what's your solar access? Again, being realistic about the trees and the shading, and that you'll be able to generate as much as you think you will. So here it is all installed. And then Jennifer can share her, that it's mostly meeting demand, but when the teenagers are all doing laundry on the same day, then we can't quite meet it with your backup.
You said it. That's true. That's true. So most of the time I can even drive on solar. Really depends on if I'm home when the solar's, but a lot of times I go to work and then my solar panels, but that's where the batteries come in. So it's charging the batteries. And then like Andy said, my house I wanted it to be as close to kind of zero net energy to guinea pig on myself. And then I was like, oh yeah, this is great. My whole home's backed up. It's all good. Except, laundry day is epic. And and this is just an example that solar only met 59% of my need that day because laundry is intense. I don't have a heat pump dryer that would help, but I do have an electric dryer that I had before, still use it, and that's kind of the downside. So when you think about upgrading, so that kind of segues into some of the resources which I want to highlight for you. Again, I'm kind of going to go large scale to small scale here. If you're part of planning and building where you're working on large scale permitting and fire safety codes, if you're not familiar with the best model ordinance and guide, here's a link, and it's just kind of, it's can be helpful for folks in planning and building departments to be familiar with this and to have that resource available. County of Santa Barbara actually has gone out of their way to create an energy assurance plan. So if you're in the County of Santa Barbara, I wanted to point this out to you so that you can take a look at this, because it's a great resource and give you more information about these things. If you're just generally in Santa Barbara County and San Luis Obispo County, or in some of the 3 counties north of us, then you might already be a part of the Central Coast Community Energy, where even though you could get your utility bill through PG&E, you would maybe also be part of the community, Central Coast Community Energy Plan. And they have an option if you wanted to say that your electric grid connection was from 100% renewables, you can opt into that with the Central Coast Community Energy. And then this is just a map showing where all those renewable resources are coming from that are being procured by Central Coast Community Energy and then fed, into the grid. And then you can participate in that to help promote more clean energy and community aggregation. PG&E now has some new resources. So if you go to PG&E's website, they now have a clean energy tab. And under the clean energy tab, you can look up more about solar, EV charging, batteries, and they have a new Your Home Electrification Project guide link. And I put the website link to it so you can download that PDF. And I thought it was great because they start out real basic, like giving you some definitions and a diagram of an electric panel. But then what I really thought was helpful is it gives you an example of how to look at electric load comparison for a house, because this goes directly back to what Andy was saying. Do you need to upgrade the panel or not. And so if you don't do anything, you don't need to upgrade your panel. But if you do a standard like electrification project and you want to get a new clothes dryer and you want to get a new heat pump heating and cooling system, etc., and maybe you're going to get an electric car with the EV charger, all of a sudden you might be looking at having to upgrade your electric panel, which can be very expensive. And so then they give you some ideas of how to reduce the need for a new electric panel as part of your electrification project. So one of those things is to purchase a heat pump dryer or a condensing dryer rather than just a straight up electric resistance dryer like what I have. The other thing is they have now their smart circuit sharing devices. So this example in the guideline references a circuit sharing device that lets you share your clothes dryer with your EV charging. And it's smart enough. It charges your car when you need it, and it uses the same circuit as your dryer. And therefore, if you do these things in combination, you may not need to upgrade your panel at all. So I spent a little more time on this resource based on those questions, but that's in there. And then if you just want to understand rooftop solar home battery solutions, maybe for yourself or your clients, and you're in the Southern California Edison, you could go to Solar Marketplace, and they have a great interaction home electrification marketplace website as part of that, so that you can start to look at what it would take. Also, Energy Sage has some great resources, and you can use their solar calculator to better understand the cost effectiveness of solar and batteries, and it will link you to some pre-screened installers, which I found to be very helpful. Also, a lot of the companies that are selling products also have great websites to help you size a battery so you can better understand the benefits, but the costs. So that kind of goes directly to some of the other questions. So Enphase, for example, has a website that will help you size a system, answer a few questions, gives you an idea of what capacity you might need or want. So you could click on the homeowner's part and then design my system. And then it'll give you some feedback on solar panels and battery, and then also kind of give you an idea of how long that battery would last, if it's cloudy or not, and if you have sun. And then Watt Plan is a really good website. And I like this one a lot for figuring out the size of a PV system and battery. And you could try our solar, and then you can fine tune your solar and battery details based on actually how much energy you're using in your house now. And you can input that in. And I use this, and it helped me figure out that I wanted to really back up my whole house. So I ended up with 2 batteries instead of 1. 1 battery is probably more cost effective, but like Andy said, we like to guinea pig on ourselves. So I did. And so far, I haven't regretted it for the convenience. Like, the power goes out, and my kids and I were getting ready for school, and the power goes out, and we're still getting ready. And come on, get in the car. We got to go. We get time. And then we look around, and it's like, oh, wow, the whole neighborhood is dark. Oh, but we're still ready for school. Okay, well, I guess you kids are going to school anyway. They may not like it. I love it. But anyways, gives you an idea of the benefit of the batteries, and you can put some cost numbers to it and understand your break-even points. And then with that, last but not least, we are code coaches. So if you have questions, you should reach out to 3C Energy, 3C Ren, for your energy code coach questions. Free service. And I'm going to hand it back over to Chloe.
Thank you so much, Jennifer and Andy. That was great, even the second time around hearing it. And we do have a little bit of time left for questions, so I think I've got a few closing slides, then I'll pass it back to Jennifer and Andy to take any questions we haven't gotten to in the chat yet or anything else you guys have. Can we go to the next slide?
Yes.
Thank you. All right, so as we talked about at the beginning of the webinar, but for anyone who joined late and might have missed it, AIA and ZNCD learning units are available for this course if you attended at least 1 hour of it. The ZNCD continuing education units are a certificate that'll be automatically emailed to you after the training if you attended enough, but those are all self-reported. AIA learning units I will report on your behalf if you have indicated you'd like those. We also recorded this presentation, and the slides and the recording will be available to you within the next couple of days. We have some exciting courses coming up, so you can take a look at those over here. But we also have the full lineup of all of our courses for the next several months on our website. So check that out if you're interested in seeing what else we have coming up. And then the last thing I'll mention is that I launched a poll a couple of minutes ago just to get some feedback on today's presentation. If you haven't had a chance to fill this out yet, I'd really appreciate it if you could. It's really helpful for us to get feedback on these programs and get a sense from our audience of the topics they're interested in and what we should offer more of and what we can change. So thanks so much, everyone, for being here. Thanks, Andy and Jennifer. And with that, I'll pass it back to them for questions.
Awesome. Thank you so much. I'll go ahead and just touch on some questions. And let's see, there was one just quickly. Somebody asked about AB 130, which is the state legislation that puts a pause on updating the residential energy code basically through that 2028 cycle. So there won't be any new, there won't be any increases to electric ready PV solar for residential construction until that next until 2031. And then if you're doing an LA fire rebuild, there's also special legislation that you can use the 2022 code. You don't have to update to the 2025 code, with the exception that you still need to make sure that you're doing the solar and solar ready requirements of the code. So hopefully that answers the 130 question. And then I did want to circle back, and once we feel everybody has seen these slides, maybe we can stop sharing and folks can unmute as needed. I wanted to check back on the kind of an early question of somebody from a building department that a project is coming in and wondering about using a battery backup for the building safety elements and the fire pump in particular. I put in the chat as a response that that is allowed, except that in our experience that once the building is at a size that it needs a fire pump, that a battery is not great at meeting that surge of energy. And so it just ends up being very expensive. Otherwise, it seems that the batteries are a great way to have regular backup power compared to a diesel generator. That one is just a fossil fuel based and has kind of those regular maintenance requirements. But I don't know if Jennifer or anybody else on the call wants to, or our original questioner wants to kind of unmute and just highlight what's going on with that project or concern.
I don't have anything. Oh, go ahead. Go ahead.
Hi, I'm Joseph Yu. I'm one of the building inspectors in the SFO International Airport. And so
Great.
the project is a new parking garage with EV ready and EV charging, but they're also making provisions for EV ready chargers. So the fire sprinklers are the fire sprinkler requirements are higher, so they installed a fire pump. But for I guess to meet their energy goals for the airport, they wanted to use a battery backup, which the code in the NFPA usually stipulates a generator. And so this is the first time one's been installed in the airport for emergency services like fire pumps or emergency power. Um, so there's just questions on um, reliability, testing, life cycles, because typically uh, diesel generators are only turned on when it's an emergency and they're dedicated. So thank you.
Right. And with the diesel generator, so as a backup for emergency, so California Air Pollution Control Board gets involved, right? So there's going to be the reporting requirements, and you'll have to turn the generator on periodically to make sure it's operating. That's part of it. And then there's certain runtime that you keep track of to see that you're staying within your emissions. But like one of those projects like that, the Santa Barbara fire dispatch project. I mean, part of what they did was to have a lot more PVs and battery. And the idea was their diesel generator would just do that maintenance like we were talking about, and then not have to solely depend on it. But part of it being like this microgrid now is that the transition between battery, generator, solar, if the grid goes down, it's all a smooth transition. So it islands. So I don't know if that helps address some of the things you'll need to look at, but I would reach out to your colleagues in Santa Barbara and see if they would be able to help you in navigating the work that they've done.
Great. Thank you.
Thanks. There was a question I started to mention just in terms of the batteries and where we're landing with the vehicles, being able to charge back up a home with a vehicle battery. I know it seems like it has such promise, but I know it keeps getting held up a little.
Yeah, yeah, it's just what you said. And
Yeah,
then, but
okay.
there are systems out there, like if you're can afford if you're in the market for a truck and you're out in a more rural area and you need a truck or want a truck, then like that's the kind of the best I've seen is for home projects is to get like the new electric truck because the battery then they say is big enough and it's got the two-way charging so you can plug it in. But then there's also a lot of companies out there now that are starting to have the control mechanisms, the controllers at the house to be able to accept, energy resources. If you email me, I can, I remember, I'd have to look it up and I could send you a link if the person wanted to know a little bit more about that. And then otherwise what we're seeing is for buses. That's the main thing I'm seeing. It's like done on a school district or community scale where the buses themselves have been set up with the two-way charging.
Yeah, they're little rolling backup batteries. I love that as
Yeah.
for schools, and then they can also. I think they're a great backup for minor medical or just resiliency centers and that kind of thing.
Yeah. And then
Great. And then the last one that I had offhand, and happy to entertain others if folks want to unmute. But the last one was just kind of a general, if you have any general comments about being grid tied, being off grid altogether. I know in general we have encouraged grid tied for the most flexibility, and that off grid is kind of more of when it's necessary to be totally off grid. But any other thoughts on that in particular, being grid tied versus off grid?
In particular, some of the challenges that we deal with in Burlingame, California is we're very tied to PG&E's grid. As of right now, one of our main avenues, which has a lot of small family-owned businesses, multi-generation businesses, and also the nearby customers, up to like about 1,000 right now, are being affected because of a power outage. Since this past Tuesday, they are out of power. So you can imagine how the mayor feels right now. I'm actually in talks with him right now to try to find a solution. The issue that we're having is, well, in particular, our company does baseload power. We actually drop power plants into cities. The one thing is we need room, we need space. And in California cities, there is not a lot of space to work with. So something that we've been trying to, I guess, encourage is slowly building up microgrids in every city, and then eventually finding a space where we can drop in a power plant and then apply or distribute power as necessary. Ideally, we would want every city to have their own power plant and then start to push power to their customers, be it enterprise, small business, or homes. But yeah, we've been having a lot of roadblocks there.
I thank you for talking about it, because a part of why we wanted to do this course is also just to help get the word out to like our greater community of people that are involved in the planning and building world, because a lot of we're seeing, at least this is, I've been seeing a lot of communities not understand the benefit of the having microgrids within those communities, how it adds to resiliency. And then they don't understand that. So then there's localized pushback against developing that system. And so I'm glad you mentioned it, because I think the more a lot of us understand that's what's going on, we can kind of help educate the other people around us. And as being part of, building specialists, it seems like that's something we should know more about. For good examples of that, I mean, if you take a look at what the work done in Hawaii and Alaska, they have amazing microgrid solutions, because for a long time, they knew that their communities had to be able to island, had to be able to self-support, and to be still functional. So yeah, thanks for mentioning it.
Interesting you bring up Hawaii, because one of our wastewater solutions that turns wastewater into hydrogen actually is one of the ones being implemented right now. So
very good. I'm so glad you joined the call. That is cool. And then, I see a comment, plug-in solar. So Via is a lot of like do-it-yourself homeowners want to be able to, and let me see if I'm catching the right comment. Jeffrey, you could unmute yourself, feel free. Like plug-in solar, meaning modular battery generator systems where you can purchase them, stack them together, get as much as you want, and plug it into your house and plug other things into it and use it that way. They exist, but I don't know much about the Utah legislation. You might have to bring us up to speed.
They recently passed a law in Utah with bipartisan unanimous support to support these low power systems. Typically, I think in Utah, it might be up to 1,200 watts of power, but you can just plug it into your circuit. And they're designed not to backfeed into the grid. Brightsaver is a company in the Bay Area that's doing a lot of work in this area. There's also some of Craftstrom is another one. Zendurance is another, Zendur actually it's called, is another one that's producing some of these systems.
And what's the status? You said the legislation was recently introduced in California. Is there was the legislation for California to just make it more like clear that it's
right now
allowable?
it's right now it's sort of in a gray area. Like PG&E is permitting some testing in the Bay Area, for instance, that Bright Saver's been conducting testing. But there isn't really a clear, straightforward, yes, you can do this. And so there's actually a legislation has just been introduced in a number of other states as well. So it's looks like it's going to, modeled on what's happening in Germany, where there's over 1 million permitted, and they think there's like 4 million systems, including ones that are not registered.
Yeah, that's what I'm familiar with is not registered ones, and they're just like doing it.
Right. Yeah.
Well, I'm looking at the time here.
Thanks.
It's after 11.
Wow.
If there's
So much
questions
fun.
that you didn't get to, you will get the slides and has our contact information, or reach out to Chloe and she'll get in touch with the right folks. So thanks everyone. Super lively and terrific information to be able to share with each other. So thanks that. And Chloe will send out both the PDF and the link for the recording. Any other
Thank you very
closing?
much.
I just
All
want to say thanks for participating. The questions were great. Thank you so much for the folks who you could add to the collective knowledge. That's really, really appreciated.
For sure. Thanks,
Thanks,
everyone.
everyone. See you next time. Bye.
Thanks, everybody.